Welcome to this video on depth first search, a fundamental search algorithm used in artificial intelligence and computer science. Depth first search explores a graph by going as deep as possible along one path before backtracking. This approach helps in exploring large search spaces with minimal memory and is useful in tasks like paths binding, solving puzzles, and graph traversal. In this video, you will learn how DFS works, how a stack or recursion drives the process, and where DFS is used in real applications. DFS works in a very different way compared to BFS. While BFS explores the tree level by level, DFS goes deep into the tree before exploring anything else. To implement DFS, we use a LIFO queue, also known as a stack. In a stack, the most recently added item is the first one to be removed. So, whenever DFS generates successor nodes, it pushes them to the front of the fringe. This ensures that the least successor, the deepest path, gets expanded next. By continually selecting the newest deepest node, DFS explores one long branch at a time, making its search behavior very different from BFS. In this example, we will see how depth first search operates on a simple tree. At level 0, we have a root node A. At level 1, A has two children B and C. At level 2, B expands to D and E, while C expands to F and G. We begin by expanding A. We generate B and C and push C first, then B, so that B stays on top and is expanded next. When we expand B, we generate its children D and E. To maintain left to right order in DFS, we push E first and then D onto the stack. This ensures that D, the leftmost child, remains on top of the stack and is expanded next. After completing the expansion of D and then E, DFS backtracks to B and then to A. From there, it moves to the next node in left to right order, which is C, and continues the search from that branch. When we expand C, we generate its children F and G. To maintain left to right processing in DFS, we push G first and then F onto the stack. This keeps F, the leftmost child, on top of the stack, ensuring it is expanded before G. By following this approach, DFS explores the nodes in the exact left to right sequence A, B, D, E, C, F, and G. Depth first search has a few important properties that shape how it behaves in different types of search problems. DFS is not complete in infinite depth spaces or in graphs with loops because it may keep going down one deep branch forever. However, if we prevent repeated states by tracking the nodes already visited on the current path, DFS became complete for any finite search space. DFS is not optimal. It returns the first solution it encounters, and that solution may not be the slowest or the least cost option. In the worst case, DFS may explore all the way to maximum depth m, giving a time complexity of big O of b to the power m. This can be very bad if the maximum depth is much larger than the solution depth. But if many solutions exist, DFS may find one quickly, sometimes faster than BFS. Space complexity. A major benefits of DFS is its space efficiency. It only needs to store the current path plus a small number of siblings, resulting in a space complexity of big O of B multiplied by M, which is linear and far smaller than the exponential space needed by the BFS.